Welcome to Mind Overboard, the channel where we take a deep dive into seemingly simple questions or interesting topics and try to provide an alternate perspective. In this video, we're going to explore the concept that there may be limitations to human knowledge or understanding through a discussion of the nature of science and the discovery of the neutrino. And this is important to examine because it's not uncommon for people only casually interested in the subject to be uncertain about trusting the results of science. We are inundated on a fairly consistent basis with early reports about studies done with subsequent results that may indicate an outcome that could have the potential to overturn a prior discovery. The finality or definitiveness of these outcomes is often exaggerated and excessively reported, burning an impression into the public psyche that often confuses what conclusions can actually be drawn. It gives undue credibility to the idea that science is not a mechanism of consistent forward progression, but an open free-for-all, where discoveries actually represent newfound ignorance and old ideas and newer concepts are constantly flopping around, gasping for breath like a fish out of water. A summarization of this sentiment could be formulated in the observation that, while there are prevailing models that explain the world around us and its natural laws, every prior model was eventually discovered to be wrong. So there's no good reason to believe that anything we think we know will remain as it is in its current state. Fortunately, the situation is not nearly this bleak, and this doesn't represent a full explanation of the circumstances in which we find ourselves. Science is a process by which we come to discover things about the natural world, utilizing a methodology intended to separate information and observation from our natural biases. And while some scientific discoveries do invalidate what came before, or lead to completely new branches of science, it's often the case that the newly emerging theory actually represents a clarification or refocusing of the predominant model. For instance, the discovery of quantum mechanics is the largest leap forward ever made, and it's been measured with a degree of accuracy that is almost incomprehensible. To say that it will never be proven wrong is nearly beyond all doubt, but it doesn't fully supplant Newtonian mechanics. Newton's physics can still get us to the moon, but it doesn't provide us a picture of reality that is anywhere near as complete as Einstein's equations. Similarly, scientists, in a continuous effort to push the boundaries, search for an elegant underlying formula that unifies the four forces of the universe. It's believed that this will provide a more complete and accurate model of the universe than the standard model. This level of accuracy and completeness is just a cleaning up of loose ends for the most part. The standard model will remain as accurate and elegant as currently measured. This explanation still leaves some holes to fill. Why would scientists believe that a unified theory of everything exists? Also, if established theories are based on experimentation and observation, why do some scientists make suppositions about mysterious elements of our universe that many, including other scientists, would suggest are fundamentally unobservable? There is discussion about the contents of black holes, objects the interiors of which don't allow access to any information. There has also been a recent surge in the promulgation of the existence of a multiverse or other universes, which would necessarily rest outside our cosmos, resulting in a similar sparseness of information. And this finally brings us to our question, which is, given what we currently know and what it seems possible to know based on our current scientific understanding of the nature of the universe, can it be said that there's a functional limit to what humans can discover or know? While it seems reasonable to presume there is a limitation on what we can know, and it would certainly be a stretch to posit that we could learn anything about the cosmos that may exist outside our bubble of information, the horizon beyond which we can never send nor receive information because it's receding from our view faster than the speed of light, this may actually be a hasty assumption. Given the things we learn every day and the boundaries we have already exceeded, it may not be safe to assume that we're in a position currently to understand in a meaningful way just how much we don't know and to what degree any of this knowledge may be inaccessible. Taking a positive approach, one could say, outside of a handful of extreme examples, setting any sort of limitations results in an assertion that contradicts our history of knowledge acquisition and scientific discovery, which is riddled with thresholds set and destroyed over and over and over again. Given this history, it could be equally reasonable to suggest that it's likely we will continue to unlock the mysteries of nature in novel and unforeseen ways through the combination of applied ingenuity and constantly advancing technology. A simple case in point to support this involves the discovery and verification of the existence of neutrinos, a type of elementary particle. To start down this path, we will begin by establishing the relationship between math and science. If it's a fact not already clear to you, you should be made aware that there is an intimate relationship between math and science. You're probably familiar with natural laws being generally accompanied by equations. It's important to recognize that these equations represent a description of the laws they reference. The most well-known example to clarify this is Einstein's formulation, E equals mc squared. This is a simple equation that elegantly describes the relationship between energy and mass. We all get that to some degree, but the part that doesn't always seem to connect for people with less than a passing interest in the subject is that the relationship being expressed here is actually a physical one. It exists in the real world and can be observed and tested. Being an equation, rules of mathematics can be applied that allow us to manipulate the terms and derive a proof. But it's not merely a process of applying rules to numbers. The fascinating reality of this process is that the steps one would take to get from the original equation to the proof describes an actual relationship in nature. If confident in the results, an experiment could be designed to try to verify this. The end result of a successful experiment would be an actual observation in nature that confirms the original hypothesis. This could produce new information to be added to the current model, or if it doesn't fit, it may require the development of a new model that can accommodate this newly discovered natural phenomenon, after it's been tested and confirmed by multiple independent parties. In other words, one could go from a purely hypothetical conjecture, expressed and verified mathematically, to a direct observation in nature. The mathematics maps onto the natural world. Math is a universal language that describes natural phenomena and relationships. This is where the neutrino comes in. In the early 20th century, we received the gift of Einstein's aforementioned quantum mechanics. Utilizing this new model of the universe, Einstein was able to make predictions about natural phenomena that would demonstrate the veracity of his hypotheses. As scientists began to take the steps necessary to test the predictions, the observational data gave an extremely strong signal supporting the model. These results attracted the attention of the physics world, causing many physicists to examine the math more intently. One result of this was Wolfgang Pauli noting in 1930 that there was an implication in the math surrounding particle physics suggesting the existence of a very low-mass, essentially chargeless particle. It was later further expanded upon and named by Enrico Fermi. This particle would travel at nearly the speed of light and would be unlikely to interact with any other particles, making it effectively invisible. It was declared that this particle, while a well-motivated implication from the math, which appeared to be accurate and was confirmed mathematically by other prominent scientists, would essentially be undetectable and unobservable. We jump now to our current state. Neutrinos are not only observable, but we have enough information about them and the ability to gather enough additional information that the study of neutrinos comprises its own branch of astrophysics. One could spend their entire career devoted to the study of neutrinos. This is despite the fact that their revealed properties are almost exactly as predicted. They are so unlikely to interact with other particles that you could trap one in a room where every wall is comprised of lead, 1 light year thick, which is trillions of miles, and the neutrino could leave the room without any indication that it had ever been there. Neutrinos are generated by the processes taking place inside stars, and there are billions of them traveling through every inch of your body every second of the day. How did we do that? Well, the odds of them interacting with other atoms is low, but not zero. It will eventually happen. Scientists devised a plan to improve the odds. So look at it like this. The odds of winning the Powerball are something like 290 million to 1. Not zero, but essentially so low you could buy a ticket, bet you won't win, and win that side bet every time for the rest of your life. The unfortunate part is that you would never get good odds on your bet because it's such a sure thing. However, if you were somehow able to purchase 145 million tickets every week, your odds look significantly better. They would essentially come down to a coin flip. You could go long stretches without winning, but would average out to winning about 50% of the time. They did this with neutrino detection by using huge underground pools of chlorine. They used deep underground decommissioned mines to minimize outside interference from other particles and radiation. Using huge volumes of chlorine increases the odds of observing a reaction. Because you're now constantly monitoring a localized source of huge quantities of individual atoms of chlorine, it's the chemical equivalent of purchasing 145 million lottery tickets. The neutrino, if it interacts with the chlorine atom, will knock an electron out of place, causing that atom of chlorine to convert to argon. One fascinating point to make, and I'm not sure how one goes about doing this, but when they failed to make an observation, it raised questions about the techniques involved and the team's ability to observe a single atom of argon among the chlorine. To demonstrate their capabilities, they successfully injected and removed a handful of argon atoms into the tank. The story is being shortened here, but the end result of this was the successful observation of a neutrino interaction. The information we gained from this allowed us to modify the mathematics to match the observation, which uncovered additional unexpected characteristics of the particle, which then segued into additional improved observational methodologies. It goes on and on. Having summited the peak of discovery, we're at the point where the information we glean now leads us to more effective means of gathering new information, with the primary limitation being our technological capabilities. To view the overall topic from a positive perspective, rather than saying that all prior theories were wrong, we could view it as all prior theories have eventually been improved or corrected. In the cases where they're completely overturned, this is usually a consequence of discovering something monumental and expecting to crash through each new threshold. On the frontier of scientific discovery, we should continue to anticipate most of our prevailing ideas to fall. This serves as a testament to our ability to progress and the importance of accepting falsifiability as a characteristic that strengthens ideas. This should cause us to be optimistic of the future. Based on what we currently know, there are certainly discoveries that appear to be beyond our grasp. Assuming we will never be able to verify the initial state of our universe, the existence of a multiverse, etc., is a safe assumption. However, it seems as though, given a sufficient amount of information and time, and looking at the way in which we've gone about discovering some of the things we currently know, human ingenuity appears to be effectively boundless. Once a process starts us down a path of discovery, there isn't much that can prevent us from achieving our ultimate goal. Not knowing where our combined efforts will take us, it seems premature to assume there's not a future point at which we will obtain a nearly complete understanding of the natural world, where no knowledge lies beyond our grasp. Do you disagree? I'd love to hear your arguments in the comments below. Thanks for watching.